Hello and welcome to a short illustration of the MBSE++ principles using Syndea. Let's start with the first principle. We are developing systems in a heterogeneous and multidisciplinary multi-vendor environment. System information exists in a wide variety of models, tools, and repositories during the lifecycle. We must be able to reach out to these repositories and models and deep dive. In this Syndea dashboard that I've launched from a SysML modeling tool, Magic Draw in this case, I can see the various kinds of repositories I'm connected to. For example, Doors repositories, GitHub, Jama, Jira, a lot of CAD models and Excel spreadsheets and Simulink models, MySQL databases, PLM systems like Teamcenter and Windchill. From within the dashboard, I am able to go and deep dive into the repositories. For example, consider the Doors NG repository here. I can expand this automobile project and look at the details, for example, modules and requirements and links between the requirements. Similarly, I can expand a PLM system here, Teamcenter, and look at its details. For example, the part structure for an automobile, as you see on the dashboard over here. We can also search repositories. For example, in this case, I'm searching a Jira repository for an issue called SDB158, all from right within the Syndea dashboard. Now let's move to our second principle. We need to have a high-level architecture of the system that can be used to coordinate the models in various disciplines. This high-level architecture also provides an entry point for systems engineering. We use SysML to represent this high-level architecture, and using the Syndea dashboard, we can create connections between the elements of this architecture and elements in various repositories. For example, we see the SysML model for this automobile here, and on the right-hand side, I can toggle back and forth between different repositories. For example, bringing requirements from Doors into SysML and being able to link them to the rest of the architecture. Alternatively, I can start with an architecture element, like here in this case, the automobile, and use it to generate a bill of materials in a PLM system in Teamcenter. That brings us to the third principle. When we do these drag and drop operations, moving information from one discipline to another, we are actually creating persistent connections across these disciplines. Model-based connections are the DNA of interoperability. In this case, we've created a lot of inter-model connections. For example, I can see connections to Teamcenter, reference connections to a variety of other repositories, connections to Doors NG, and others. While we're seeing inter-model connections, that is the connections crossing the boundaries of model elements, in this case architecture to PLM to requirements management to issue tracking and project management, there are also intra-model connections. For instance, in this case, the satisfy relationship from the automobile block in SysML to the requirement in SysML. We should also think about the purpose of creating these connections. Connections can have patterns. For example, a reference connection creates a simple hyperlink that can track versions of elements that have been connected on either side. A data map connection, on the other hand, can track versions, but in addition can also track attributes of elements. A function wrap connection can wrap executable code, track its changes in versions, re-execute the code, and bring back the results. The model transform connection can track all of the above, plus it can also track the multi-level nested model structure. So we must select a connection pattern based upon the level of interoperability we need with the discipline. When things change, these connections help us track what has changed and where. For instance, if I right-click on this automobile block in my system architecture model, I can run a compare function across all the connections to the different disciplines that this automobile may have. And that results in a comparison table like this, which can say, for this automobile, I'm connected to a Jira issue which has been updated. I'm also connected to a Teamcenter item, and I see that the suspension as a part of the automobile exists or has been added in the PLM system, but it doesn't exist in my architecture model. At this point in time, we can decide to synchronize in either direction depending upon the privileges that we may have. Let's use the sixth principle as a starting point and also deep dive into the fourth and the fifth principle. Experts working with models in their own discipline also need to trace to models in other disciplines. For example, a system engineer working with SysML needs to trace to 3D CAD models for mass information. A mechanical designer working with CAD or PLM information needs to trace back to system level requirements. To facilitate the visualization of these kinds of relationships, from within the dashboard, we could launch this chord diagram that can show all the connections I have in my system. This is what we see as part of the total system model graph that has been presented earlier. In this case, we see SysML elements in purple, for instance. They are color coded as we see on the right hand side, that are connected to a variety of elements in other repositories. For example, in this case, they're connected to requirements coming from Doors NG, they're connecting to software code coming from GitHub, they're connected to elements in my local file system, and they're also connected to issues being tracked in Jira and to parts in a PLM system. This core diagram is actually showing us all the inter-model connections, that is, the connections that are crossing the boundaries of the tools. It is not showing me the intra-model connections, which we'll get to in a moment. In this core diagram, I can see the total number of connections as the connection model analytics. I have 48 connections here across 78 artifacts. I can filter connections by selecting or unselecting specific repository types. And if I hover my mouse over a connection, I can see more details, as we see over here on the blue box coming up. Alternatively, we can start with a specific element, in this case a block in a SysML model, which is this automobile block, and look at all of its connected artifacts. And here we can see both inter and intra-model connections. This graph now shows us that the purple node in the middle is the SysML block for the automobile. It has got part properties to other SysML elements, which is what we're seeing on the first top part of this graph. It has also got a satisfy relationship to a requirement in the SysML model. These are all intra-model connections, connections that are within the boundaries of the SysML tool. But in this case, I see the SysML block is also linked to a part in Teamcenter and to a Jira issue SDB 158. The red circle indicates the element with which we started exploring this graph. I can zoom out and zoom in into every part of this graph. The green circle indicates that there's maybe more information about that node. And if I click on it, in this case, this is the automobile block in SysML that has a satisfy relationship to a requirement in SysML. If I click on that, I can now see other information about that connected requirement. For example, if I zoom into that SysML requirement, I can see it has got its own child requirements, as we see with the purple arrows, but it also has a relationship, a connection, an inter-model connection to the same requirement module coming from Doors NG. Another kind of visualization is this tree graph, where I can start with a SysML element, in this case the SysML block for the automobile, and its part properties to other SysML blocks, and its inter-model connections to Jira tickets and Teamcenter parts. If I expand a specific SysML block, in this case the braking assembly, I can see its child blocks, in this case the suspension part property, and the braking assembly part in Teamcenter to which is connected to, and the Jira ticket which is tracking its development. I can do the same for other parts in the system. In the context of MBSE++, we're building the total system model graph that we can see here. The total system model graph includes both inter and intra-model relationships to provide complete traceability and impact analysis. That was our fourth principle. Cinder provides a framework to achieve this. Once we have the graph, we can start to deploy graph reversal techniques such as breadth-first, depth-first searches, and Dijkstra's algorithms to perform quantitative impact assessments. That brings us to the close of this short illustration of MBSE++ using Syndea. We hope you enjoyed listening to it and seeing the demonstrations here. Please contact us for further information.